Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. Often, it's the work carried out by others that gives us inspiration to expand our research. Inspired by a review article and some more specific studies, one research team at North Carolina State University has now created a proof-of-concept high-performance imaging spectrometer which functions without external gratings or filters and could be suitable for portable diagnostics and wearable sensors. Using organic components, the spectrometer has a low power requirement and is sensitive to wavelengths ranging from ultraviolet to near-infrared. A unique feature of the design is back-to-back diodes. Dr. Harry Shricks, lead author of the study, explains why this is important.
The main part of the design is basically two photodiodes put together with what we call like a back-to-back design. So then when we sweep through the voltage, essentially we're switching the detection from one side, one of the photodiodes in the stack, to the other one. So the two important layers in each of them is the active layer, the photoactive layer. Those are the ones that are sensitive to the different wavelengths of light. We chose those materials carefully so that they absorbed light in certain wavelengths for each of the two photodiodes, to where they're alternating the wavelengths in which each of them detected, so that when we swept through the voltages, we could very clearly tell what wavelengths of light were increasing the current on which side of the detector.
Dr. Shricks mentioned choosing materials that absorb at different wavelengths. This is where organic components have an important role to play, as Professor Brendan O'Connor describes.
What's nice about the organics and the unique aspect is that they have these distinct absorption bands that have these absorption features. They're not constant absorption coefficients over that spectral band. They have this kind of structural feature in their absorption characteristics. And so designing the detector, the tandem detector, using the organics that have these complementary absorption characteristics is the novelty on the device side.
A reconstruction algorithm is used to determine the spectrum of the incident light, having first been trained using known wavelengths of monochromatic light. The algorithm accounts for noise and instability in the final solution to produce a spectrum. The next step is to utilize machine learning algorithms to refine the spectral features.
The main thing is that you have a unique responsivity at each voltage step. Once that is trained into the system, then you have input light that gives a current signature at each voltage, and then through the reconstruction algorithm, then you're able to parse out what level of what wavelength of light was part of that input.
The spectrometer exhibits a detectivity of 1.4 terajoules, which is similar to that of commercial sensors, and a responsivity of 0.27 amperes per watt. These are among the highest in the organic detector field, but the standout feature is the low power.
Other demonstrations that have tried this spectral reconstruction, they use a phototransistor design instead of a diode design, where you end up needing very high voltage inputs to do a sweep. And you also need a third lead. So instead of just two electrodes, you would need a third input. Ours just has those two electrodes, and you're able to sweep it just within 1 volt, which is an order of magnitude lower than other designs.
This initial design can now be further optimized by focusing on the selection of materials to improve the bandwidth as well as the architecture of the stack. The detector could also be scaled down to make it suitable to produce an array. While a traditional benchtop spectrometer is a powerful analytical device, this more portable design has applications in environmental monitoring, medical diagnostics, quality control, and more. Its miniature size means that it could also be used in more everyday scenarios.
If we can scale this down, make it cost effective, put it into a commercial product, then we've had that power of a spectrometer in everyone's hands. And then you could do stuff like look at your food at the grocery store and see if there's any mold there. You could look at potential healthcare applications, and maybe you can look at your skin and detect a mole and see if there's any issues that you want to look at exploring further. If you have a garden, maybe you can look at the plants, or if you're in agriculture, and you can use it to image plant leaves to see if there's any disease, early disease detection, more than what our eyeballs can do and more than what an RGB camera can do. It could also function as an RGB camera. And so it could adopt all the things of a typical CCD camera, but add a lot more power through that spectral capabilities.
This work was published in a recent issue of Device. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at mrsbulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.